Hello everybody. In the last session, we discussed at length how we go about obtaining the mathematical representation of circuits. We saw that there were three essential steps to be followed in the process of obtaining the mathematical representation. The first being identifying the energy storage elements. Second, we identify the state variables associated with the energy storing elements, and then one energy storage element by element we go about obtaining the dynamic equations around the particular energy storing element, you making use of the Kirchhoff's voltage law and the Kirchhoff's current law, that is the KVL and the KCL. That is the general procedure for obtaining the state space equation. In this session, I would like to introduce a degree of complexity in the circuit. The process is essentially the same, but just so that you should be able to do any given circuit, you should be able to obtain the mathematical representation for a circuit which is of any degree of complexity. I will introduce now as complexity which will bring in some intermediate variables which you need to address and use that to obtain the state equations. However, the intermediate variables will be used only to obtain some intermediate equations, otherwise the state equation representation, the state equation, the standard form will not be altered. So, now starting with the circuit, now let me take a circuit which is of the following nature. Let us say we have a resistance, let us have an L, then a capacitance, so this is one part of the circuit, this is the series, all are in series, this is one loop. Now I am going to connect few more components, another resistance and a resistance connected to ground. So, we have one more loop there and we have, let us say, one more inductance and a resistance and probably a source. So, we could consider a circuit which is something like this. We have a source VI1 and another source VI2, two sources. Let us have the parameters. We have the parameter here, let us say R1, this is L1, this is C, R2, R3, L2, R4 and the source VI2. So, this is the circuit. So, you see that there is a loop here, there is another loop here and there another loop here. So, there are three voltage junctions and there are two nodes here. Okay. One node is at this point, another node is at this point. Okay. So, the first step in our process of obtaining the state equations is identify the energy storing elements. So, here you have L1, C, L2, 3 energy storing elements, and therefore there has to be 3 differential equations to describe the circuit. So, L1, L2 and C, these are the energy storing elements that we need to be bothered about for the dynamics, and then identify the state variables associated with these energy storing elements. So, coming to L1, so it is the current through L1, which is, let us name it as IL1. So, IL1, and then the current through L2, and let us name it as IL2, and then the voltage across C, we will name it as VC, voltage across C. And let us also indicate these state variables in the circuit. So, we have IL1 here, let me indicate this as IL2 here. Notice that I have put direction, an arrow direction for the current flow here. It could as well be the other direction, no issues there. The sign will automatically get changed in the equation and you will not face any problems as such. Okay. Now, the third state variable is across the C, the voltage across the C, that is VC. So, now we have the state variables, the input variables and the parameters all listed on the circuit, and therefore, we should be able to make or obtain the state equations. However, here there are 2 nodes here. This node voltage is defined, which is VC, but this node voltage is not defined with a variable. So, this could give rise to a problem. So, that is the reason where we need to introduce a new intermediate variable. We will come to that as we formulate the equation. Okay. So, now the third point or the third step in our process of obtaining the mathematical representation of this circuit is we take the dynamic elements or the energy storing elements one by one and try to solve the equations around them. So, first we take the equation around L1 dIL1 by dt, and then we take the equation around C dVC by dt, and then we take the equation L2 dIL2 by dt. So, these are the 3 dynamic equations that we need to formulate, which will finally describe your system, in this case this particular circuit, completely. So, now we start formulating the equations. Let us go back to the circuit here. Let me delete these portions so that I can start writing the equation right here. Okay. So, first we take L1 dIL1 by dt should be equal to the voltage across L. Now, the voltage across L by Kirchhoff's voltage law should be equal to the algebraic sum of all the other voltages. So, let us see the other voltages which are there in this loop. There is the source voltage in this direction. So, if the current is assumed to be flowing in this direction, we have the voltage across the resistor in this direction, and of course, the inductance voltage in this direction. In fact, we need to find the voltage across the inductance. Now, what is this voltage here? This is in terms of the state variables IL1 into R1. So, now we have the equation which is very simple. We have VI1 minus IL1 R1 minus Vc should add up to the voltage across the inductor, such that the sum of the voltages, algebraic sum of the voltages in this loop, in this voltage junction, is 0 by Kirchhoff's voltage law. So, this is our first equation, and now the second equation C. Now, the equation for C is C dVc by dt, which should be equal to the current through C. Now, the current through C is IL1 minus the current through R2. But what is the current through R2? This node potential minus this node potential divided by R2 will be the current through R2. But we have not given a variable to this node potential. Therefore, we shall now introduce an intermediate variable at this point in a different color, and let me call it as Vx. So, with this now intermediate variable being put there, we have the current through C, which is IL1 minus current through R2, which is Vc minus Vx by R2. This is the current through R2, and by Kirchhoff's current law at this node, the sum of IL1, the current through R2 and the current through C should algebraically add up to 0. So, this is the second equation, but of course, here this equation is in terms of the state variable Vc, state variable IL1 and a variable Vx. We should later on express Vx in terms of state variables. Of course, we will come to that one. Now, if you look at this potential Vx here. Now, the potential Vx here is nothing but Vc minus the potential across R2, or in other words, if we assume that there is a current flowing in this direction, then we have a potential here which is in this direction as shown, and this is the potential Vx. So, now Vc plus Vc minus Vx by R2 being the current which flows through this, okay, into R2 is of course Vx. Of course, this is a trivial equation which we can't do much about that. Let me go to the new page. Let us select, go to the previous, and now let me copy all these things, copy, and then we go to the next page, paste. Okay. So, we have the circuit here, so that we again can proceed with our operations. So, now coming to this node here, what is the current that goes through R3? It is this current plus this current, meaning the current through R2 and the current through IL2, which is going through R3. And therefore, that current into R3 is going to be Vx. So, Vx equals I in IR2, that is the current through R2, plus IL2, which is the state variable here, into R3, or what is VR2? VR2 is nothing but the potential difference across this by R2. So, Vc minus Vx by R2 is the current through R2, plus IL2 is the current which is the state variable which is coming as the inductor current IL2 of L2. This whole thing into R3 is Vx. Now, if you see, Vx is the only variable here in this equation, and then Vx can be expressed as a function of Vc and IL2, which are again state variables. So, basically Vx can be expressed as a function of the state variables. So, let us see what happens. Now, again I want to select this portion. Let us copy, go to the next page and paste. Now, let us solve this for Vx, which will turn out to be Vx plus Vx R3 by R2 equals Vc R3 by R2 plus IL2 R3, and Vx is equal to Vc R3 by R2 plus IL2 R3, this whole thing multiplied by R2 by R2 plus R3 from this equation. So, from here this can be obtained. So, we see here that Vx is nothing but Vc, function of Vc and IL2 both being state variables and some parameters. We could further simplify this. Let me use the selection tool, take this to the next page, copy, go to the next page, paste. So, Vx equals Vc R3 by R2 plus R3 plus IL2 R3 R2 by R2 plus R3. So, this is the equation for Vx, which is the intermediate variable that is expressed in terms of state variables. Now, coming back to the circuit here, we need to express the third equation, which is given here as, let us paste it here. Now, the third equation is the equation for L2. L2 d IL2 by dt is equal to the voltage across L2. Now, the voltage across L2 is obtained by, now the current is flowing in this direction, let us say that is there is a effort here like that, there is the effort of the source which is like that, the current direction is assumed in this way, and therefore, we have the voltage across R2 in that form, in that direction, and the voltage across L2. And the voltage across R4, of course, we know this is IL2 into R4, and the voltage across this is nothing but Vx. So, therefore, we have I2 minus IL2 R4 minus Vx. This is the equation, the third equation. The first two equations we saw is here. The first equation is here, L1 di L1 by dt, which is equal to the input and this state variable and two state variables IL1 and Vc coming into the picture there. The second equation is Vx, sorry, it is not this. The second equation is the C dVc by dt equation, which is equal to the current through the capacitance, which is IL1 minus Vc minus Vx by R2. Here there is this new intermediate variable coming into the picture. However, we have shown that the intermediate variable can be expressed as a function of the state variables, which ultimately is given in this fashion: Vx as a function of Vc a state variable and IL2 a state variable. And the third equation is this, which is revolving around the dynamic element L2, which is L2 di by di L2 by dt is equal to Vi2 minus IL2 R4 minus Vx, and Vx again is the intermediate variable, which is same as that expressed as So, which means all three equations are expressed as functions of input variables and state variables only, the intermediate variable being expressible in the form of state variables. So, this is this extra effort that needs to be done in some of the circuits where some of the nodes is not directly a state variable. In such cases, the intermediate variables can be used for such nodes or probably branch currents, as the case may be, and it will definitely be expressible in the form of an equation, an algebraic equation, which is a function of these state variables, some or all of the state variables. Okay. Now, these equations 1, 2, 3 can now be put in the standard form of x dot, which is equal to Ax plus Bu, and y, which is equal to Cx plus Du. In this case, the state vector x is the state vector which is IL1 Vc IL2. This is the state vector. There are 3 state variables. U is the input vector which consists of 2 Vi1 and Vi2. So, you will find IL1 dot IL2 dot two dot, I made a mistake here, I apologize, Vc dot is equal to the A matrix, which is basically the function of all the parameters of the circuit, the R1, R2, all those things. And you have IL1 Vc IL2 plus the B matrix and Vi1 Vi2. So, here actually the A matrix is going to contain 3 by 3 elements. The B matrix is going to contain 3 rows and 2 columns, as shown, and the output y, whatever the output y is supposed to be, will contain the C matrix IL1 Vc IL2 plus we have Vi1 Vi2, and as there are no direct feed forward terms, that is 0 and 0, and here if it is Vc that we want to consider as an output variable, then it would be this 0 1 0. So, this would be your C matrix, this would be your D matrix, this is your B matrix and the A matrix, all expressible in the standard state equation format. So, now we have obtained the mathematical representation of the circuits. Whatever may be the complexity of the circuits, now we will be in a position to obtain the mathematical representation, that is in the state equation form, either by using intermediate variables or even without, depending upon how the circuit topology is. Now, having once obtained the mathematical representation, what do you want to do with them? Now, you have the state equations with you, which gives you the dynamic behavior of the circuit. Now, what do you want to do with these mathematical equations? We need to analyze them. We need to analyze the equations so that we get a better insight into the circuit. So, now we have the model. The model is in the form of a mathematical equation. Which is in our case the state equation. Now, with this model, we would like to now analyze the circuit. Analyze the circuit. Now, the analysis of the circuit before was being done manually, that you do a hand calculation, probably plot the graphs and then try to get the details or the features of the circuit. But now there are a lot of computer softwares available which will do the bulwark of doing the computations and then plotting the graphs. So, we need to supply, of course, the mathematical model that you would have obtained, like we discussed just now. And in the process of analysis, there are few points that I would like to mention, that the analysis is generally done in 3 domains or viewpoints. One is the time domain. The other is the frequency domain, and the third is the pole 0 domain. Should be noted here that the circuit, the signals, all these are existing in the time domain only. However, the designer or the analyzer or the person who is analyzing can view the system or the signals by jumping to other domains, and that is the frequency domain and the pole 0 domain, to obtain some useful information about the circuit or the system or the signal, which may not be so easily detectable in the time domain. So, in the time domain, we are plotting everything always with respect to the time as the x axis. the y axis would be an amplitude. It could be a current wave shape, or it could be a voltage wave shape, or any other wave shape which is evolving with respect to the time. It could be the response of the system also, like a step response. Like if you give an input as a step, how will the output evolve? The output probably evolves like that, and so on. So, these are the issues that we can see, the characteristics of the waveform in the time domain, like the rise time. The rise time, or what is the peak overshoots, or what is the steady state accuracy or the settling time, how long the response of the system takes to settle down after the step has been initiated, things like this. Now, these are some of the parameters that can be directly read out from the time domain wave shape. In the frequency domain, the information that is not directly evident in the time domain is the harmonic contents, the frequency spectrum, and how the gain of the system varies with frequency. These are some of the characters which cannot be obtained directly from the time domain response. So, in the frequency domain, one would like to plot the waveforms with respect to the frequency omega. Omega is basically the radian frequency. Here, there are two major plots that need to be viewed. One is the magnitude plot, and the other is the phase plot with respect to the frequency omega. Meaning, how does the absolute value of the gain vary with frequency? Is it a low pass filtering effect, and at what frequency will the 3 dB point occur? At what frequency the zero crossover occurs? So, these are important characteristics of the magnitude plot. What will be the gain or the attenuation of a particular circuit at various frequencies? So, corresponding to those frequencies, what will be the phase plot and how does it look like at various frequencies? Is it going to be in phase, or is it going to be having no phase shift with respect to the input waveform? Is the response having 90 degrees phase shift, 180 degrees phase shift with respect to the input waveform? These are issues that you can obtain. These are the information that you can obtain from the frequency domain plots. And then the third domain is the pole 0 domain. So, in the pole 0 domain, it is a Cartesian coordinate system where the x axis is named sigma and the y axis is omega, and any point in this coordinate system S is sigma plus j omega, and this is called the S plane. So, the S plane is basically a representation of the physical system which will give you an idea of the poles, location of the poles, zeros of the system. The poles of the system are nothing but, in the time domain, the exponential behavior, that is e to the power of, that is if there is a value a pole of value a only, then this will result in a time response of e to the power of minus a t. So, we know that if there is a disturbance in the system, now that disturbance will decay with this time constant, a time constant which is 1 by a. So, each of the pole point here represents an exponential decay mechanism, such that any disturbance or an excitation will decay at a particular rate. Now, this gives lot of insight about the system's dynamic behavior and the disturbance rejection behavior, which will not be obtained from the other two domains. And this domain will also give you a good aid to position your poles and zeros such that any disturbance and any noise rejection and any decaying properties can be planned and designed, and thereby the values of the components parameters can be chosen. Of course, it should be noted that in a physical system all the poles and zeros will exist only on the left half of the S plane, because only in the left of the S plane any pole or a zero would have e to the power of minus a t, which decays. But if it is on the right of the S plane, let us say a point B, then it would have a time domain response e to the power of b t, which means it is growing with time. Any disturbance will not decay, but grow with time, as b is positive and it is an unstable system, and therefore, it is not a system which can exist in nature. So, all physical systems will have poles and zeros located on the left half of the S plane, and how close or far away from the omega axis or the y axis will determine the features and characteristics and the damping ratios, decaying nature, all those issues which can be used for synthesis of the circuit. So, therefore, we have three major viewpoints. Any system, any circuit will exist only in the time domain. However, apart from being viewed in the time domain, meaning the response of the circuit, apart from viewing it in the time domain, the response can also be viewed in the frequency domain, and also there is one more domain which is very important in characterizing the system, which is the pole zero domain, which describes the system in a slightly different way in the S plane, which gives you a behavior of the excitation capability, the decay of disturbances, the decay of the noises, the decay of a sinusoid, the amplitudes of a particular disturbance which will affect the output. All these issues can be studied from the pole zero configuration or the pole zero pattern on the S plane. And one could also design the values of R, L's and C's such that the pattern of the pole zeros can be modified to suit a particular design requirement or a design specification. So, these are the three domains that one should be able to move about and understand for any mathematical representation or any model. And one should seamlessly be able to jump from time domain to frequency domain to pole zero domain, pole zero to time domain, so on and so forth, without much problems. Then the understanding of the whole system or circuit will be more complete. Now, what we shall do is to analyze the system. And we said that we are going to analyze the system in these three domains, that is the time domain, the frequency domain, and the pole zero domain. And to analyze, as I was saying, there are many software packages available, and out of which for this discussion and all the future discussions we will mainly be using the MATLAB Simulink environment. So, the MATLAB Simulink environment is what we will be using for doing most of the bulwark of the analysis. We of course will provide the model, that is the mathematical representation of the equations that are the equations that we have obtained from the circuit after having done the process of the state equation extraction. So, let us take a simple example circuit. We had previously in the last session worked on a very simple RC circuit. If you remember, recall that this RC circuit was was modeled, and the state equations for this were also obtained. So, this of course has the direction as shown. You have the voltage across C and it is a state variable, and there is one equation here which is given by C dVc by dt, which is equal to Vi minus Vc by R. So, dVc by dt is the current through the C, and which is nothing but Vi minus Vc by R. Or putting it in our standard form, Vc dot will be equal to minus 1 by RC into VC plus 1 by RC into Vi, and let us say V naught is our output, which is given in this form, plus 0 into Vi. So, we have our A matrix, the B matrix, the C matrix and the D matrix. So, what is necessary to be inputted to the software environment is the A matrix, B matrix, C matrix, D matrix and the values of the parameters R and the C. So, if you go into this MATLAB computational environment, the command window looks like this. This is the MATLAB command window. This is where all the equations are typed in and the results are viewed. This is an interpreter based language. So, you could probably type in some variable equals 2 into something, it will compute like an interpreter. You could also use these variables for something else, like for example, another variable b, which is a to the power of 3, something like that one. So, this is how the computational environment works. Now, this is very suitable for our purpose of analyzing the circuits, which are of course being represented as state equations, and the mathematical equations can directly be ported in here. Like for example, let us say R is equal to 10 ohms, R equals 10 ohms, C equals let us say 10 microfarads. Therefore, I am writing it as 10 E minus 6, and then the A matrix can be written as within the brackets, square brackets, minus 1 by R into C. This would be the A matrix, and the B matrix is nothing but the negative of the A matrix, which is like that. And of course, the C and the D matrix are very trivial, which is like that, and D matrix which is 0. So, in this way we can enter and obtain the 3 matrices, which is the A, B, C, D. D matrix. Now, once the A, B, C, D matrices have been entered, they can now be used for all the manipulations, mathematical manipulations that the software permits, which of course I will discuss that in some detail in the next class. Coming back to the board here, there are 3 domains, as I told, the time domain, the frequency domain, the pole 0 domain. After having inputted the A matrix, the B matrix, the C matrix and the D matrix into the MATLAB, we will use 3 major tools. One is the step function to obtain the step response of the system. The second one will be Bode or the frequency, to obtain the frequency and the phase plot of this particular system that you have modeled. And third, the PZ map, which will give you the plot of the pole 0 location of the system. So, these are the three main functions that we will be utilizing in trying to analyze the system and trying to get the features of the circuit that you have modeled. So, in the next class, we will try to input the mathematical models of some of the circuits that we have already obtained the state equations for, and in MATLAB try to analyze the system in the time domain using the step function, in the frequency domain using the Bode and the pole 0 map to obtain the pole 0 domain properties. So, the step would be for the time, Bode for the frequency and PZ map for the pole 0 domain picture. So, we close the session at this point. Thank you.